This lesson is on circular motion. Most of us have all experienced circular motion. Anytime that you ride in a car and you go around a curve, you're experiencing circular motion. You might have, at some point in your life, rode on a carousel. You may have even at an amusement park rode on a swing ride that swings you in a circular path. So at some point we can draw on our experience about circular motion. Normally, if we were to push an object in a horizontal surface, the natural path that it would follow would be that of a straight line, a linear path. We know that objects have inertia, which means that an object in motion will stay in motion unless acted upon by an outside force. So an object in motion will continue to follow its direction of motion until acted upon by an outside force, which means that in order for an object to follow a circular path, an outside force must exist, pulling the objects around the curve. In order for an object to make a turn without a steering wheel, something must be pulling the object inward at every instant of time in order to be making the curve. Let's consider an object following a circular path. Let's put Freddy, and I can't attempt to draw Freddy, so I'll draw Freddy as a circle. Let's put Freddy on a string. We'll give him some arms and legs and head. There's my attempt. And Freddy's attached to a string. And let's allow Freddy to swing around the circular path in a circle attached to the string. So at every instant of time, as Freddy is moving around the circular path, he's being pulled inward by the string. So this is at time equals 0, and we'll say that this is at time equals something greater than 0. We'll just say 1 second later. So in order for Freddy to make the turn, he has to be pulled inward by the string. The string is keeping Freddy in his circular path. The string provides a force that pulls inward on the object, making the object turn. Later on in this lesson, you'll learn more about this force. It's called the centripetal force. But where would Freddy go if the string were to break? If the string were to break at this instant of time of 1 second, Freddy would fly in a path, a straight line path, from that point forward. Freddy's velocity is tangent to the curve of the path. We also call this tangential velocity. Again, something we'll talk about more later in the lesson. So at every instant of time, Freddy is being pulled into the circle, but his motion is wanting to move off the curve in its straight line path. A little bit later in time, Freddy is being pulled into the curve by the string, but wants to move tangent to the curve. You'll notice at every instant of time that Freddy is being pulled in and wanting to move outward with a tangential velocity. These vectors are all at right angles to one another. Okay. So as Freddie's moving around the circular path, he obviously has velocity, and his velocity, which is a vector quantity, has a direction. The direction is tangent to the curve, and this direction of Freddie changes every single instant of time, because each instant of time, Freddie is now pointing in a new direction. His direction is constantly changing. So please remember, as we go through the lesson, that the velocity is changing due to change in direction. So this is a little different from the changing velocity that we spoke about in previous lessons. It's not that the speed is changing. Speed, which we use a lowercase, I'll make that a little bit better. We use a lowercase v to denote speed with circular motion. Speed doesn't have to change. The speed can stay constant even though the velocity is changing. And the only reason why the velocity is changing is because the direction is changing. Speed is scalar. Speed does not have direction, so therefore speed can remain constant. And velocity can change because the direction is changing. So this is our new concept for this lesson. Centripetal acceleration is the acceleration of the object toward the center of the path. We know from Newton's second law that force produces acceleration. Force produces acceleration. The centripetal force we just spoke about is responsible for producing the acceleration of the object. We also know from Newton's second law that the direction of the acceleration is in the same direction as the force. So if the centripetal force is inward, that means that the acceleration is also inward. Centripetal acceleration is calculated by two variables. The centripetal acceleration is calculated with the formula A of c equals v squared over r. This v that we're speaking of is the speed of the object around the path, and r is the radius of the circle. So the centripetal acceleration is calculated by the speed around the path and the radius of the path. So let's look at the relationship between centripetal acceleration and speed. Centripetal acceleration and speed are both in the numerator of the equation. So since they are both in the numerator of the equation, they have a direct squared relationship. Direct because they're both in the numerator, so as one increases, the other will also increase. But because v is squared, acceleration will increase exponentially. So as speed increases, acceleration increases in exponential fashion. Again, you're going to see this equation manipulation we started with last topic with universal gravitation. If we double the speed of an object, what happens to the acceleration? Well, let's see. A of c is equal to 2v squared over r. Whatever happens to v has to be squared, so if we bring our 2 squared out, of our equation, we have 4 over 1. What you do to one side, you must do to the other side. So the centripetal acceleration will quadruple. If the radius is doubled, what happens to A of C? So this time, instead, we'll take double the radius instead. I don't know what just happened there. So let's double the radius instead. And now we have, whoops. And now we have 1/2 outside our original equation, and we do the same to the other side, 1/2. So if we double the radius, we half the acceleration. So now's the part of the lesson that you kind of miss out on with this video lesson. My demonstration, I put some water in a bucket and I swing it over my head, and we watch as the water does not spill out of the bucket. Unfortunately, you'll have to be in class to see that. If the speed around a circular path is maintained, does the mass of the object that's moving in the circular path affect the centripetal acceleration? In other words, if I have a heavier object, will it affect the amount of centripetal acceleration? Well, let's look at it this way. The centripetal acceleration is calculated by looking at the speed of the object and the radius of the circle. So, does mass directly affect the centripetal acceleration? No. The mass of the object, if the speed were the same and the radius of the circle were the same, the acceleration of the object would also be the same. There is a catch, of course. You're saying, well, this probably doesn't make a whole lot of sense because a more massive object would not accelerate as much as a lighter object because it would require more force to keep it in the circular path. You would be correct. Mass does not directly affect the acceleration of the object, but in order to maintain the same speed, we must increase the force for a more massive object. So we can say that if the speed is maintained and mass changes or increases, decreases, the force would have to increase in order to maintain that constant acceleration. So a lot of the reason why we bring this up in the lesson is because a lot of questions ask about how mass affects centripetal acceleration, and the answer is it doesn't directly affect acceleration. What it does affect is the force that's required to maintain the constant speed. As I described before, the centripetal force is the force that keeps the object in its circular path. It is the force responsible for producing the centripetal acceleration. We know from Newton's second law that force produces acceleration. So the centripetal force produces the centripetal acceleration. And they both act in the same direction, which is inward. So remember, this is the first time that we have a constant speed, but a changing velocity. So that means that we have a constant speed with acceleration. And it's only because that velocity is constantly changing. And in order for it to change, an outside force must act on the object in order to change its direction. The formula for centripetal force is F of C equals mass times centripetal acceleration. All forces are measured in newtons, mass is measured in kilograms, acceleration measured in meters per second squared. we can replace A of c in the same equation with its formula, which is v squared over r. So we end up with this formula for centripetal force as mass times v squared over r. You can add this to your reference table for future use. Okay. A lot of the questions pertain to the diagram of centripetal motion. You notice that in this diagram, F of c and A of c, the centripetal force and the centripetal acceleration, act in the same direction, which is inward, pulling the object towards the center of the path. That is what creates the curve, and that is what produces the circular path. The velocity of the object, you can see, is tangent to the curve. The velocity is directed in a straight line path off the point of the curve, creating a tangent line. So this is the velocity. Speed doesn't have a direction, so if you were to label the speed, you could label the speed around the curve of the path. And the velocity vector and the centripetal force and acceleration vectors, they make a 90-degree angle with one another. Okay. A couple other things to label on the circle. We know that the circle has a radius, and we also know that the distance around the circular path is called circumference. We also should know how to calculate circumference. Circumference is equal to 2 pi r. So we could technically be given just the radius of the circle and be expected to find the speed for the circular object, or for the object rounding the circular path, where the distance around the circular path, d, is the circumference of the circle, and t would be the time that it takes to travel around the circular path, which we also call period. Period of revolution is typically denoted with a capital T instead of a small t for time. And remember that the direction of velocity is always tangent to the curve of the path. Now let's try this example. A track player has a hammer with a mass of 4 kilograms, moves along a circular track of radius 1 meter at a speed of 5 meters per second. First, we want to determine the acceleration of the ball. We can do that very easily. A of c is equal to v squared over r. The speed of the hammer is 5 meters per second. We need to square that. And the radius of the circular path is 1 meter. 5 squared is 25. 25 divided by 1 is 25 meters per second squared. So now we have the centripetal acceleration of the hammer. The centripetal force of the hammer is simply mass times acceleration. The mass of the hammer is 4 kilograms. The acceleration we just found, 25 meters per second squared. 4 times 25 is 100 newtons. All forces are measured in newtons, no matter what type of force we're talking about. In this example, we have a satellite who is a very large Freddy. Freddy is 50 kilograms, and he's orbiting around the Earth 1,000 meters above the Earth's surface at a constant speed of 100 meters per second. Again, we're going to find the acceleration of the object and the centripetal force keeping him in the circular path. The only difference here is we have the added radius of the Earth, which we'll need to look up on our reference table. So not only do we have this distance above the Earth's surface of 1,000 meters, we also have the radius of the Earth, which is found on your reference table. The mean radius of the Earth is 6.37. Let's see, 6.37 times 10 to the 6th meters. That's the radius of the Earth. We'll need to add the distance above the Earth's surface for the total radius of the circular path. So we just need to add 1,000 to 6.37 times 10 to the 6th. So we see that it doesn't add too much to our value for the radius. Adding the 1,000, it makes the number 6.371 times 10 to the 6th meters. Okay. Now, we need to determine the acceleration of satellite Freddy. Speed of Freddy is 100 meters per second, that's going to be squared, over that total radius from the center of the Earth, 6.37 times 10 to the 6, oops, forgot the 1, meter. All right, make sure you use parentheses when you're calculating. So you should pause and calculate the acceleration. You should have gotten 0.00157 meters per second squared. Okay, now we're asked to find the centripetal force for Freddy. We simply multiply the acceleration that we just found by the mass to find the centripetal force. Centripetal force would be 50 kilograms multiplied by the acceleration of 0.00157 meters per second squared. Centripetal force is therefore 0.0784, 5, we'll make it 5. Oops. I don't know. That's not the right thing. There we go. I'm having trouble. 5. Just make that a 5. Newtons. Okay. Easy as pie. I forgot when I did this, but you can see that I did draw a perfect circle. We checked it with my circle maker, and it's pretty close. You can see where I started and where I finished, but I think I did a pretty good job. Right now I need you to take out your Prentice Hall books and work on page 49, numbers 88 through 96, 100 through 103. They all pertain to circular motion. Let's review the questions. For 88, in question 88, we have a 2 kilogram cart in a circular path, traveling at 6 meters per second, and the radius of the path is 3 meters. We're asked to find in 88 the magnitude and direction of the centripetal acceleration. AFC is equal to v squared over r. We have the speed as 6 meters per second squared over the radius of 3 meters. 36 divided by 3 is equal to 12 meters per second. Okay, 89. In 89 refers to the same problem. Calculate the magnitude of the centripetal force. F of c is equal to m a of c. The mass of the object is 2 kilograms. The centripetal acceleration we just found, square on that acceleration, 12 meters per second squared. 2 times 12 is 24, and the units for force are newtons. Okay. All right, let's go on to 90. With number 90, they ask what would happen if the mass of the cart were doubled. If we have 2 times the mass, what would happen to the magnitude of the centripetal force? F of c is equal to m a of c. So if we double the mass, we have 2 times the original amount. We'll bring that out here. So we have We have 2 outside, and we have to balance that. So the force is doubled, which is choice 2. For number 90, we have, 91. If the radius of the curvature of the path were doubled, what would happen to the centripetal acceleration? A of c is equal to v squared over r. So if we double the radius, we have to bring 1/2 outside, and we have to do the same thing to the other side. So the centripetal acceleration is halved, which is choice 1. Number 92. If the speed of the cart were doubled, the magnitude of the centripetal force would be what? I'm going to use the combined formula that we talked about in class, mv squared over r, where v squared over r is the centripetal acceleration. If we were to double the speed of the cart, anything we do to v is also squared. So 2 squared is 4. We'll bring a 4 outside. We have to do the same thing to the other side. So the centripetal force is quadrupled. Choice 4. Number 93. If the mass of the cart were halved, what would happen to the centripetal acceleration? Centripetal acceleration is v squared over r. Mass is not in the formula, therefore if we change the mass, the centripetal acceleration does not change, which is choice 3. Remains the same. Does not affect A of C. Number 94, they ask, in the position shown in the diagram, towards which point is the centripetal force acting on the cart? Centripetal force is always acting inward to pull the cart around the centripetal circular path. So F of C is pointing in towards point D is in there. Okay. It says also in 95, in the position shown in the diagram, towards which point is the velocity of the cart directed? They show the speed is going around the circle this direction, so the velocity is going to be tangent to the curve, which is pointed towards point A in the diagram. Okay. Number 96. Which factor, when doubled, would produce the greatest change in the magnitude of the centripetal force? F of C equals mv squared over r. So we can look at all of these factors. We have mass, we have radius, we have speed, and we have weight. Weight would be related directly to mass. So it's basically the same thing as choice 1. So the greatest change would occur whenever we change whatever is being squared, which is speed in this case. So if we change the speed of the cart, it'll affect the centripetal force exponentially and directly related. So choice 3. All right. Let's move on to questions 100 through 103. You have a cart. They change the direction of the speed. The speed is now clockwise. A radius of 2 meters, and the cart is here. And they ask towards which point is the velocity of the cart directed at in the position shown. All right, so we're looking for the velocity. If the cart's going around this way, the speed is that way, the velocity is going to be tangent to the curve at that particular point, and that is towards point S. In question 101, towards which point is the centripetal acceleration? Centripetal acceleration and centripetal force both act in the same direction. Force produces acceleration, and therefore they have the same direction. So A of C and F of C are both pointed inward toward point Q. In question 102, if the mass of the cart were doubled, what would happen to the centripetal acceleration? As explained before, the speed and radius are the only factors that affect the centripetal acceleration, and therefore mass does not change the acceleration of the object, so it is choice 1, unchanged. And for 103, the magnitude of the centripetal force acting on the cart is what? Well, we have some information from the problem. We have 5 kilograms as the mass. We have the radius of 2 meters. We have constant speed of 4 meters per second. And so we need to find F of C, that is equal to mv squared over r when we combine our formulas. Substituting in, we have 5 kilograms times the speed squared, over the radius of 2 meters. And so therefore we have 4 squared is 16. 16 divided by 2 is 8. 8 times 5 is 40 newtons. All right, so this concludes our Prentice Hall review. All right, so you do have homework. Prentice Hall, page 63, 29, 30, 32 through 34, 88 through 91, 93, and 171 through 178. So it is homework, but you should have time in class today to get at least half of this done. And I'll see you tomorrow. Bye.